So cyclic group on a set of G. The group G is called as cyclic group if for any A belongs to G, every element of that G is obtained from generator A. So every element of G is in the form of A raised to n, where n is some integer. The element A is called the generator of G. So if you see the example, consider the group G which containing the element 1, 2, 3, 4, 5, 6 under the multiplication modulus 7. So in this example, we have to find multiplication table of G. Second, they given that find inverse of 2, inverse of 3 and inverse of 6. Third, find the order and subgroups generated by 2 and 3. And fourth, given that we have to find out whether the group G is cyclic group or not. Now set is given element 1, 2, 3, 4, 5, 6. So we will first create a matrix, multiplication matrix under modulus 7. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, multiplication of this and modulus 7 is applied. So 1 into 1, 1. 1 modulo 7 is nothing but 1, 2 modulo 7 is 2, 3 modulo 7 is 3, 4 modulo 7 is 4, likewise. Then you can see that 2 into 4 is 8, 8 modulo 7 is 1, then 10 modulo 7 is nothing but 3 and 12 modulo 7 is nothing but 5. Likewise, we obtain all the elements from this matrix. Now inverse, for finding the inverse of this element 2, 3 and 6, we should be know which one is identity element in this matrix. So in this multiplication operator, so identity element in this algebraic structure is nothing but 1. So you can see that left identity, that is nothing but row identity, is nothing but 1. So here you will get the same element after multiplying this 1 to this 1, 2, 3, 4, 5, 6, and column identity is nothing but this one. So when I want to find the inverse of 2, then I will see in the row of 2 where the output is 1. So here output is 1. So we know that element into that inverse element will give the identity element. So in this case 2's inverse is nothing but 4, 3's inverse is nothing but 5, then 6 inverse is nothing but 6. So these are the result for this inverse element. Now second question they given is third question is given is that find the order and subgroups generated by 2 and 3. So order and subgroup generated by 2 and 3. So 2 is, if you consider 2 as a generator, 2 raised to n, n is nothing but any integer. So 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 1. It is by this table. So 2 raised to 1 is 2, 2 raised to 2 is 4, again this 4 is taken for this, 2 raised to 4 is 1, then 2 raised to 1 is again 2. So likewise you will get the same element repeatedly, so then you have to stop. Here it is there is some modification in this. See there, 2 raised to 1 output is 2, then that n value is taken as a 2 for next iteration. 2 raised to 2 is equal to 4, then 4 should be here, so 2 raised to 4 is equal to 1. You can see in this table 2, 4 value is nothing but 1. So likewise you will get these values: 2 raised to 3 1, 2 raised to 4 2, 2 raised to 5 4 and 2 raised to 6 1. So order is mod 2 is equal to 3 and group is equal to group generated or group obtained by these two generated 2 is nothing but 1 comma 2 comma 4. If you take a 3 as a generator then a value is nothing but 3 and a raised to any integer, that is 3 raised to 1 is equal to 3, 3 raised to 2 is equal to 2, 3 raised to 3 is equal to 6, 3 raised to 4 is equal to 4, 3 raised to 5 is equal to 5, 3 raised to 6 is equal to 1. So order is 3 is equal to 6 because you are getting 6 distinct elements, 1, 2, 3, 4, 5, 6, and after that it is repeated. So order is mod 3 is equal to 6 and group is equal to 3, group generator is equal to 3. So G is a cyclic, generator of G is nothing but 3 in this case. Now next concept is nothing but group homomorphism. So when two groups we can say that homogeneous or homomorphic. So let A comma dot and B comma star be a two algebraic systems. So these are the two algebraic systems. Then a homomorphism from A comma dot to B comma star is a functional mapping f A implies B such that fx into y is equal to fx into fy. So example, let's see, A1 is one algebraic system, so on operator that is multiplication, and A2 comma dot, this is some operator. B an algebraic system. Determine two algebraic systems are homomorphic or isomorphic. So these are the two algebraic systems as they given. It is on multiplication, it is on dot. They given values also. Set of input is A, B, C, A comma B comma C for this first algebraic system, and this for this A2 set contain the element 1 comma W square. So A into A output is A into B, B, A into C, C. It is given. So in this case A is nothing but the identity element. If you see, B into A is B, B into B is C, B into C is A, C into A is C. So this is given things. Here 1 is nothing but identity element. If you see the this output of the matrix, then if you see function A is equal to 1, function B, function A is equal to 1, means when you are giving input to the function as a you are getting the output as a 1. When you are giving the function input to the function as a B, it will give the output as a W, and if you are giving input to the function as a C, then output is W square. Then f A into B is equal to f A dot f B. F A into B, by this table you will get A into B is nothing but B, so that is nothing but FB. FA, you are aware with that, it is 1. FB is nothing but W, so 1 dot W. And if you see the plane FB, that is also W. So left hand side is equal to right hand side, so WW. And if you see FB into C, it will give FB into FC. So FA, so B into C is nothing but by this matrix, B into C is A, so FA, and FB is we are aware that is W, and FC is nothing but W square, so FA is equal to 1, and W into W square by this matrix, W into W square is also 1, so it is also matching. The LHS is equal to RHS. So what they ask is determine two algebraic system are homomorphic or isomorphic. What is the condition? Two algebraic systems, that is A comma dot and B comma star, is a functional mapping f A implies B such that fx into y, x means fx dot y is equal to fx into fy, and this is matching here, so these are the homomorphic. These algebraic systems are homomorphic. Now, what is meant by isomorphic? Isomorphic means two algebraic system, let G1 comma star and G2 comma dot be two algebraic system where star and dot are binary operation. Binary operation. If the system is homomorphic and in addition f is 1 to 1 and on 2, then f is called as isomorphic. Means initially you have to check given system should be homomorphic. For homomorphic, we see the condition that this fx dot y should be equal to fx into fy. Then it is called as a homomorphic. And if the system is homomorphic, along with that, if that algebraic system satisfying addition f is 1 to 1, in addition, if f is 1 to 1 and on 2, f is called as a isomorphic. Means whatever the function that is given, if it is 1 to 1 and on 2, then it is called as isomorphic. What is meant by 1 to 1? Means for every input of the function, it should give unique output from the domain. In that case, it is called as 1 to 1. And what is meant by on 2? All the domain values should be occupied, then it is called as onto. So if these both conditions are satisfied, then it is called as isomorphic. Next is automorphism. And isomorphism of a semi-group onto itself is called as a automorphism. Means there is an algebraic system which is isomorphic, then then semi-group onto itself is called as a automorphism. Two groups are equal, then it is called as a automorphism. So here these are the different properties on the group: homomorphism, automorphism, isomorphism. Now next important structure, algebraic structure, is nothing but ring. So up till now we seen that what is meant by semi-group, second monad, then we seen group. After that we seen abelian group. After abelian group we seen these different properties of the group, and now the next algebraic structure is nothing but ring.